We'll start just like nothing has happened. Okay, so we need to, first of all, think about what you've learned before. You have learned about arithmetic sequences and series. An arithmetic sequence might be something like 1, 4, 7. What's the next number if it's arithmetic? 10, 13, and so on. An arithmetic sequence is one where you are continuously adding, right? Add 3, add 3, add 3. You can represent arithmetic sequences with linear functions. Okay? Because you could say the first term is a 1, and then I'm going to repeatedly add 3. Right? Repeatedly adding 3, you represent it. If you want any term in the sequence, you take a 1 and you add 3 times something. If you wanted the fourth term in the sequence, you probably called it term 4. You call this one A. How would you get term 4 from A if you knew the difference? You usually use the D for difference. Term 4, you take the first term. How many times have you added the difference? You've added it 3 times. 3 times the difference. If you wanted term 10, you take the first term and how many times have you added the difference to get to term 10 up here? It's going to be 9 times the difference. I'm not sure if you remember that from grade 10 or not, but you did learn that kind of concept. Here's the trick. To write it in general terms, term n was the first term plus, it wasn't n times d, it was n minus 1 times d. And I'm not sure if in grade 10 you put the d after it or before it. This was a general term formula for a term in an arithmetic sequence. We are now looking at geometric sequences. I'm not sure if in grade 10 you made the connection between arithmetic sequences and linear functions. This is a pattern like that, 1, 4, 7, 10. If you graph that, 1, 4, 7, 10, it forms a linear function, except that it's discrete values. What that means is discrete values, separate points instead of this. This you could, a continuous line here, you could use to represent a quantity that's continuously changing, something that's steadily increasing. If you have a container and it's filling up with liquid, the levels, if the level's going up here, this is continuously going up, right? The amount of water. Actually, there's a way we can do that far better now that we're recording it. No, forget it. Not worth playing around with that. I think you understand that if you have a tank of water and the level's going up, it's continuously going up. You could talk about the time at 0. There's a certain amount of water in it to start with. You could talk about the amount at 1. You could talk about the amount at 2, or 1.5, or 1.72. All the values along here mean something. That's different than this. This kind of a graph up here would represent, let's say you had, this is the amount of something you had every week. This is week 1 and week 2 and week 3 and week 4. Do the in-between points mean anything here? Do they mean anything? Can you talk about week 1.5 if you're counting weeks? No, you can't talk about week 1.5. You just say there's the first week or the second week. This is discrete data, discrete values. The in-between points don't mean anything. In grade 10, the type of problems you represented with arithmetic sequences were where you had discrete things where you counted. The other thing that you need to know, and this is fundamentally why this is one off of what you think it might be. Like for the 10th term, you're adding 9 times the difference. Whereas if you try to write a linear function for this, it's just whatever the value is. After time is 10, you add on 10 times the difference. The fundamental difference is when you're counting things, you start with 1. Right? When you're counting things, you go 1, 2, 3, 4, 5. You do not start with 0. Whereas when you're measuring continuous time here, if you're thinking of a stopwatch, you start the stopwatch with the stopwatch starts at 0, right? Not at 1. If you're counting time continuously, you start at 0. Whereas if you're counting individual discrete items, you start at 1. So what does that mean about what we're doing here? We're going to do a parallel thing here. Is we're going to look at the connection between geometric sequences and exponential functions. That's why they're in the same chapter of that textbook, if you're using the textbook. But there's a connection here. You could talk about $1,000, and someone is going to give you 10% more every year. Now, we actually modeled that kind of a problem with exponential functions, but it's probably better modeled with geometric sequences, because in your bank account, you have an amount of money after 1 year, and after 2 years, and after 3 years. It doesn't grow like this. Your money does not grow as, here's 1,000, and it grows continuously. It isn't that every instant they're giving you interest. Probably the only time it makes sense is at the end of 1 year, you have this much, and at the end of 2 years, you have this much. In actual fact, it probably does this. It's $1,000 until they pay you the interest, and it instantly jumps up when they pay you the interest, and then it instantly jumps up again. But we don't necessarily want to make it that complicated. So we could think about it as discrete values here. Whereas if this was a population growing, populations grow continuously. It's going up throughout the year, not all at the end of the year. So the types of problems we're going to look at with geometric sequences are where you have discrete things. Let's make it even simpler here. Let's say you get paid $1,000 in month number 1 that you start a job. The first month you start a job, you get paid $1,000. And every month after that, you get a 10% raise. So what would you get paid in month number 2? 10% raise. You get how much? What do you get paid here? 10% raise. You can do this. Come on, what's 10% of 1,000? $100. So in total you get paid $1,100 in month number 2. This is even tougher. Month number 3, 10% raise on this. What's a 10% raise on that? You're adding on $110. 1,200, 10. I don't even want to ask you this. Add on 121. 1331. This is if it was month number 1, month number 2. We're going to compare this to, let's say you had a population. Okay? This is a population. This is your pay each month. Okay? Your pay each month. This could be the exact same problem if it was population. If it starts at 1,000 people and grows at 10%. Population grows continuously. It's going to look like a graph like this. Your pay is discrete values. You have pay in month number 1 and pay in month number 2, but you don't talk about your pay in month number 1.5. If we were making a chart for this, at time equals 0, what population do we have? You have 1,000. After 1 year has gone by, what's your population? If it's growing at 10%, you got that same value over there. After 2 years, you have 1210. After 3 years, you have 1331. The difference here is if you're counting discrete objects like months, you're counting the months, what do you start counting with? If I ask you to count the people in this room, the first person you're going to say is 1, right? Whereas if you're counting continuously, if you're looking at something continuous like time, you start measuring time with 0, right? Are we clear on the difference there? The hard part, or the reason I bring that up is because in this case, after 3 years, how many times have you multiplied it by 10%? After 3 years here, how many times have you multiplied it by 10% for the population? 3 times, right? So you would take your starting value, times it by whatever rate you're using, and you'd raise it to the power of t, I guess, or n, or whatever you're counting it as there. Whereas for this situation, in month number 3, how many times have you multiplied it by 110%? How many times have you added on 10%? In month number 3, how many times have you gotten a raise? Twice, right? 2 raises in month number 3. Okay? 2 raises you have in month number 3 here. We're going to have to stop that.